Ok, bonjour. Merci d'être venu. Welcome. Thank you for coming. So, last time we derived the equation of motion for the Green's function. In other words, we took the time derivative and it acts on the theta function that are in the time-ordered product. And there's also a term that comes from the derivative of the field operator psi, so that gave this here. And we worked very hard to get this contribution. Okay, because it depends. Inside, there's not only the Hamiltonian, but there's also the time-ordered product of the integral that involves the phi. And when we compute the equation of motion for the field, there's a commutator of the h minus mu n with psi 1. And in the interaction term, what happens is that basically you get rid of two psi dagger and get delta functions. And because there's a psi dagger 2 here, at the end we have a psi dagger 2. And then when we just stare at this equation, we see that we have the definition of sigma now. Because from general principles, we know that G has the structure of 1 over G0 minus 1 minus sigma, right? Which is the same as saying that G is equal to G0 plus G0 sigma G. And this is also the same as saying that G0 minus 1 times G is equal to 1 plus sigma G. So all of this is, you have to think of this in terms of matrix multiplication. So sigma G is equal to this. Now, today we are going to see how we get these pictures here from these algebraic equations. And in the end, what is nice is that you can get the algebraic expression just by staring at the pictures in the end. But we derive everything algebraically. And when we are used to it, we will we'll work directly with the pictures. And so you see why the pictures are useful for observables. So for example, suppose we want the density correlation function, okay, which we saw we can measure with energy loss, electron energy loss spectroscopy. So you see you have already a density here, and then if you take psi dagger equals 1 plus, then you put it this way, and that becomes density correlation function. So these 2 points have to be together, and these 2 points have to be together. And how do we compute this? Well, we have the Green's function there, and we have an iterative equation for that plays the role of a self-energy for this density correlation. And this, we know what it is. That's the functional derivative of sigma. And we have an expression for sigma. So for example, if I take the functional derivative of this term here, it just gives me an interaction and then an interaction. So in other words, we have everything here to build every quantity we can be interested in just from the Green's function and the interaction. Okay, so in quantum mechanics, it's the Green's function that's important because you have to look at particles, and if you have density, then the particle can propagate from psi to a psi dagger, or a psi to a psi dagger. That gives this, or if you want, it can do this from psi to psi dagger. So we have everything we need there. So the plan today is that I will derive this equation from this functional approach. And then this gives me the expression for the self-energy. So I will have the expressions for the self-energy. Then we'll go to the most important or first approximations we learn about, namely Hartree Fock and random phase approximation. Random phase approximation will be to compute the density. And eventually we will see that it will help us to compute the self-energy in the so-called GW approximation. So we will see what the Hartree Fock and RPA look like in space-time. So again, just looking at diagrams, we will see what we need to do. And finally, we'll move to momentum space. So eventually, we agree that there is translational invariance. So phi is equal to 0, translational invariance, and then we can work in momentum space. And then these diagrams we will interpret in terms of momentum instead of just positions in space-time. Okay. So are there any questions? So is the plan right? Okay, is it clear? Yes, okay. So what we have shown already is that if I take the functional derivative of G12 with respect to phi 3,4, that was equal to psi dagger 3 psi 4 times psi 1 psi dagger 2. So that if you remember, there was the time order product of the exponential of psi dagger psi times phi. So the functional derivative with respect to phi gave me this psi dagger 3 psi 4, and G12 was already there. And then we need to functionally differentiate the denominator also. So that gave plus G1 3 G 4 2. So that came from the derivative of the denominator. I hope I get this right. I think this is G12, sorry, G12, G43. Okay. So how can we get a closed equation for this object? Well, we can, it's very simple. We just use the fact that G times G minus 1 is equal to 1, okay? And you have to think of this as matrix multiplication, remember? So it means that delta G delta phi times G minus 1 plus G times delta G minus 1 delta phi is equal to 0. So it means that I can write delta G 1, 2 delta phi 3, 4 is equal to minus G 1 G 1 let's say 5 bar delta phi of well, let me go a little bit more slowly. Delta G minus 1 5 bar 6 bar delta phi 3 4 times G of 6 bar 2. Okay? You see that I have the product of I multiplied by G from the right here. So that gave me to the left minus G delta G minus 1 times G. And this is all like matrix multiplication. And I did functionally differentiate with respect to phi. And now G minus 1, I know G minus 1 is there, and there's some phi dependence here. So there's a first term that comes from this phi. And G minus 1, you can read from this. And you take G0 minus 1 minus phi, and you put the minus sigma on the other end. So G minus 1 is this minus sigma. So the first term is this times delta phi, 5, 6, 3, 4. And I have another term which is just plus G1, 5 bar times delta sigma. The minus sign disappeared because this minus sign over there, delta sigma 5 bar, 6 bar times delta phi 3, 4 times G of 6 bar 2. Okay, the G is attached to this. Now you see that the sigma is a functional of G again. There's no explicit phi dependence in sigma. One way to see it is that delta sigma, delta phi is related to all these things that involve only Green's function. So what we do is we use the chain rule here. So this is delta G 7 bar 8 bar times delta G 7 bar 8 bar times delta phi 3, 4. Okay, so we have derived this equation. You see, I have delta G 1, 2, 3, 4. I write like this. Now, what will happen here? This will put 5 bar equals 3 and 6 bar equals 4. Okay. So 6 bar equals 4, and this is 3. 3, 4. Okay. So I have G13 and G42. Okay. So these two labels were together, so they're still together here, and 3, 4 at the bottom. Okay. So these are these two Green's functions. And then I have this. Okay. So I have G of 1, 5 bar and G of 6 bar 2, with again these two things on top. And then I have 3, 4 here, and this is G of 7 bar, delta G of 7 bar, 8 bar. So 7 bar, 8 bar, 3, 4. Just like here, I have 1, 2, 3, 4. Now I have 7 bar, 8 bar, 3, 4. Okay. And this red block here is this. So the red block, 5 bar, 6 bar, 7 bar, 8 bar is the functional derivative of sigma with respect to G. Okay. So now, if I just see this, I can just write this. Okay. And the rule is that you see that you have to integrate over all the intermediate labels. So there are two labels. There are 4 labels in, right? 2 in, 2 out, if you want. So 2 in, 2 out, 2 in, 2 out, and everything in the middle has to be integrated over. Okay. So we're done with this here, with the 4-point function. Now all that we're left with is this self-energy. So for the self-energy, I would need, it would be very convenient if I had a bigger board, but what can I do? That's it. Okay, so the self-energy, I can read from here. So I will, by having this equals this. So I will write that sigma 1, 3 is equal to minus this. So V1 minus 2 bar times the time order product of psi dagger 2 bar plus psi of 2 bar times psi 1 times psi dagger of 4 bar phi times G minus 1 of 4 bar 3. So you see, I manipulated everything as if there were, as if we had matrices. In other words, I started from sigma of 1, 2 bar, if you want, times the G of 2 bar 2. And then I said, okay, let's multiply by G minus 1. So this will be 4 bar. So that's why it became 4 bar times the G minus 1 of 4 bar 3. Okay. So this gives me what? This gives me delta of 2 bar minus 3. Okay. So now I do the integral over 2 bar and I get 3. That fine? Okay. So so now I know how to compute this because I worked it out here. So I know that this will be equal to, looks as if the blue is doing a better job. So let's try the blue. So this is give me minus V1 minus 2 bar times delta G of 1 4 bar times delta phi of 2 bar plus 2 bar. But I have to be careful because there is this term also. So there is minus G of 2 bar plus 2 bar times G of 1 4 bar times G minus 1 of 4 bar 3. Okay. So this thing here is this expectation value. Okay, because I have this expectation value, I have to put this on the left. And I've changed the indices. So you recognize that when I take the partial derivative with respect to phi of 2 bar plus 2 bar, I get this. And I started from 1 4 bar, so I have 1 4 bar. And then I have the part that disconnected part that comes from the denominator. Okay. So let us do the the algebra here. Okay, I'm sorry, I have to do that, but I have to get rid of this. There's no more space. Or what should I do? Yeah, I'll do that. I hope I don't regret. This is very good exercise for the arm in the morning. Okay, so now there's a first term that comes from this here. Okay, so the minus times minus is plus. So I have sigma 1, 3 equals to V1 minus 2 bar times G of 2 bar plus 2 bar. No, this is backwards. I'm sorry. This should be 2 bar. You see the indices are reversed here. Big mistake. So the plus goes with this guy. Remember, the plus tells us what, at equal time, what order should we have. Okay, plus here. And then this gives me delta 1 minus 3. Okay, so what is this term? This term is the first one here, is this one. Okay, we get G of 2 bar plus is this one. And the V1 2 bar is this. So V1, I mean, here there's a delta function, delta 1 minus 3. And when we are at the vertex here, at the same place, there's a delta function. So delta 1 minus 3. So this term is called the Hartree term. So it is the electron interacting with the background. Okay, now how do we get the rest? Well, we get the rest by using this expression here for delta G delta phi. So let's write this. So we have minus V1 minus 2 bar, and okay, delta G1 4 bar 2 bar plus we can read from here. Okay, because so it means that we have G. Like this is the first term. So we have G of 1 3 bar. G of 1, I'm sorry, there's no 3 bar. G of 1 2 bar plus. Okay, this is 1 2. We have 1 3 here. 1 3. So we have 1 2 bar plus. And G of so we have 4 2. So this is 2 bar 4 bar. 2 bar 4 bar. That's the first term. And then we have this. We have this term. So we have plus G of 1 7 bar times delta sigma of 7 bar 8 bar delta G of 5 bar 6 bar delta G of 5 bar 6 bar delta phi 2 bar plus 2 bar times the G. But the G is attached to this. So G of 8 bar, 4 bar. Okay. Here we had 1 4 bar, and here it's the same. We get 1 4 bar. And remember that we had like matrix product. So 7 goes with this, 8 goes with that. And here we had delta sigma delta phi, but we used instead the chain rule. Okay. So, and then we need to multiply all of this by G minus 1 of 4 bar 3. Okay. I can get rid of this. Times G minus 1 of 4 bar 3. Okay, so what will happen here? A number of things. So here 4 bar, so that will give me that 3 delta of 3 2 bar. Okay, and then I do the 2 bar integral, and the 2 bar integral will just tell me that 2 bar is equal to 3. So you see, I have 3 equal 2 bar. Then I do the, so that I get delta of 3 2 bar. Then I do the 2 bar equation, and then I get 3 here. So I can get rid of this, and I get the 3 here. Okay. And this is 3 as well. Okay. So this first term here is so-called the Fock term, F-O-C-K. So it is this term. And there's a minus sign. Okay. So minus V13, G13. Okay. I can read it off just from this plot. And the minus sign is there. Okay. And then there's one more term, which is this mess here. So there's a minus V13, and then what we will do with this is that 4 bar is equal to 3 here. Okay, so when I do this integral, this becomes equal to the 4 bar means that 3 will be equal to 8 bar. I get delta of 8 bar 3. So that disappears. 8 bar becomes equals to 3. And 7 bar, just to be consistent with the picture there, 7 bar is just a dummy integration variable, so I can replace by 4 bar if I want. And then you see I have this term. I have V13. What did I do there?
Yes, you replaced for the first term, but then
that was okay for the first term, but not for the second.
Yes. Yes.
Sorry. So so it's only the first term that I replaced by 3. Okay. Okay, so we survive. So we get minus 1, 2 bar. Then we get the G of 1 4 bar. That's this. Then this block here is delta sigma of 4 bar 3, delta G 5 bar 6. And this whole thing here is delta G 5 bar 6, delta phi 2 bar plus 2 bar. Oof. Okay. Okay, after a couple of mistakes, finally made it. Okay, so this will stay on the board for a while because, as I say, I mean, we'll have a number of approximations that will be based on this. Let me not erase too quickly here. Sigma 1 3. Okay, just what if we just wanted to do perturbation theory? Okay, What if we want to do just perturbation theory? Then you see I have the Hartree term and the Fock term, which are just these two terms. Now suppose I want to go to second order. How can I go to second order? So the second order term, there will be two contributions, right? Because this is already first order in V. This. So it means I can compute this block here to first order in V as well. Then I will have second order. This I can get from the zeroth order, which is just this. Okay. So if I do this, block to first order, well, it was equal to this. But this is the self-energy. I need to functionally differentiate. So if I take the functional derivative, it means I get rid of the 2 bar plus here. So if I look at this expression, 4 bar 3 delta G 5 bar 6. So it means I write, so I need delta G of 4 bar 3 times delta G, sigma 4 bar 3 times delta G 5 bar 6 bar. Then, so this is V of 4 bar minus 2 bar times delta G of 2 bar plus delta 1 minus 3 times delta G of 5 bar 6 bar.
Is it delta 4 bar minus 3? Because you have to replace the 1 by the 4.
I replace the 1 by 4. And then
also in the delta.
Oh,
delta
yeah.
1.
Yes, sorry. Yes, very good. 4 bar 3. So this means that you see I get V of 4 bar minus 2 bar times delta of 2 bar minus 5 bar times delta of 2 bar plus minus 6 bar times delta of 4 bar minus 3. So in summary, what I get is just this piece here. I just get this, where I have 4 bar and what happened to 3? It's here. Okay, 4 bar 3. Okay, so it's 3. Yeah, 4 bar and 3 are really the same coordinate now. There's a delta function for the two. And at the bottom here, 5 bar, 6 bar is also the same. Okay, so I can just write 5 bar, 6 bar. So I get this. I get this, and I'm sorry. This is a dashed line. And then I get these two Green's functions there. I get this, I just replace by this. So I get this. So, and there is an overall minus sign. So, no. There was a minus sign there, and then when I differentiated, in the end, let me just draw the final result. Okay, the final result is this. I can write it like this if I want. And then I need to functionally differentiate the Fock term here, so there would be an additional minus sign. So there's this one is minus and this one is plus. And then when I do everything, it will look like this. So I come in here, I go out there, and here I come in here and I go out there. Okay. So you see how it's done, right? I did not do it properly here, but I mean, it's in principle, it's not more difficult than this.
So could you remind us what those terms are the derivative of? Is the full derivative of the sigma in respect to a g? Is that it?
Yes, it's equal to
Yes, okay.
it's equal to this.
Yeah, okay. I was just lost track. Thanks.
That's the first term. That's the term that came from this. So that's the term that came from that. And then there's another term that comes from this, which I didn't work out, but you see how to work it out. I mean, it's just doing what I did there. Okay. And in the end, the diagrams that you get are this. Okay. So you can just you have 0.1, 0.3, and then you have 5 bar, 6 bar. So you have to integrate over 5 bar, 6 bar. And here you have 1 and 3, and you have 5 bar and 6 bar. Okay, so this perturbation expansion that we get, I mean, the other day we had problems with the NSA with the destruction and creation operators. We had problems with mathematicians because of delta 1 minus 2. Now we have problems with the coroner, I mean, with the police, because this is called skeleton expansion. Okay, so what that means is that these Green's functions here are dressed. There are no self-energy insertions in the Green's function. If I did the expansion in terms of the bare Green's function, which is this orange thing here, then to second order, I would get, you see, I could get self-energies on these terms here. So I could get terms that look like, for example, okay, so this is this term here, and I could have, for example, this. That would be another second order diagram, okay? And this, like this, would be another second order diagram. And this times this would be another second order diagram, and this times this would be another second order diagram. Okay, I would dress all these things. So there's no problem in generating the series either for the skeleton or for the bare Green's function. For the bare Green's function, the rule is simply that you have to remember that this G here, this Green's function, this is becoming more and more messy. So this G is equal to G0 plus G0 sigma G0 plus G0 sigma G0 sigma G0 plus etc. And you know, this sigma itself is either first, second, or third order. It becomes a mess to follow all of this, but in principle, you can do it order by order. If you do Feynman diagrams, usually you can do it with dress G, but usually people do it with G0. So what you get are diagrams like this. And then you get rules for drawing diagrams. The rule is that here there's a minus sign for every order in perturbation theory. So here there's -1 times -1, so -1 square. And there's a minus sign for every loop. So there's an overall minus sign. This one is second order and there are no loops, so there's a plus sign. Okay, so there's, and then you have, I didn't do it for these, but you can see this one is the second order, so there's no minus sign, but there's one loop. So there's an overall minus sign, and you can continue like this. Or with this approach, well, the signs are there explicitly. You can see there's a plus sign here, a minus sign, so you can follow everything algebraically. It comes automatically. Okay. So that's the Hartree Fock approximation. Then for sigma is just this. Now, if we want to do the random phase approximation for this, so we will do the random phase approximation for the density correlation function. Okay, again, skeleton diagram just means that there are no self-energy insertions in the diagram. All the Green's functions themselves have no self-energy. And the self-energy is called one particle irreducible, which means that you cannot cut the diagram in two by cutting a single Green's function. It just remains attached. Donc, en français, c'est irréductible à une particule. Puis les diagrammes, les diagrammes squelettes. Et la self-énergie, ça continue à s'appeler la self-énergie. Okay. So, if I want, for example, the density correlation function, which is measurable, as we said, and which will come naturally in the dielectric constant and a number of other physically relevant quantities, then it means that I just put these two things together. So so suppose I want the density correlation function. So I will put one let's say 1 plus or 1 plus 1 like that, and 2 plus 2. Then this is equal to this. So now these two lines are joined together, 1 plus, and they come together like this. And 2 plus 2. So they just start from the same point. So that's the first term. Now here, what I will do is I will use the Hartree approximation for the self-energy to compute this. So there will be two contributions. The one that comes from here is just given by this. So I have 1, 5 bar, 6 bar, and I have 2 plus 2. Okay, I showed you how you functionally differentiate this to get this irreducible vertex. So this was getting rid of this. Now with this, I get the Green's function going the other way. I'm sorry, the interaction going the other way. So it will look like this. So now I can iterate this equation. And that's called the random phase approximation. Actually, if I take this into account, it's called the extended random phase approximation. The random phase approximation itself neglects this term, and we will see why it's justified, or at least partly justified, in a moment. Okay, so this is the Hartree Fock, the random phase approximation in space-time. So we go from 1.1 to 0.2, 0.1 to 0.2, etc. So, but what we want really is to take into account, take advantage of the fact that we have a translationally invariant system. So it means that now we can put phi equal to 0 and assume that everything depends only, just like the potential here, even the Green's function depend on coordinate differences only. Okay? So if we do this, then it means, for example, that means that the G1 minus 2, now you see, now I put phi equal to 0. I forgot to put the phi's everywhere here, but it would have been a mess. So 1 minus 2, because we have translation invariance, we put phi, we have these equations we derived with phi, but we can put phi equals 0 at the end. So that's what we're doing now. So this is equal to temperature times the sum over Matsubara frequencies, and from minus infinity to infinity, integral d cubed x1 minus x2 of e to the minus I k dot x1 minus x2, whoops, plus IKN times tau 1 minus tau 2 times the Matsubara Green function. So it says g of k and IKN. Okay, and now I will change the notation a little bit. Here I will put the spin here explicitly as a label like this. So 1 minus 2 does not include the spin anymore. Okay, so I just use the translational invariance to see that G1 minus 2 is equal to this. Okay, and these are fermionic Matsubara frequencies. And I can do the same for V. But for V, remember I introduced delta of tau 1 minus tau 2. And so it will be the same, except that we will have bosonic Matsubara frequency. Okay, everyone is happy with this? So the purpose now is to write this in momentum space. Then that will be easy to work, easier at least to work with, instead of having a Green's function in space-time. We take into advantage that we take advantage of the fact that we have time and space, well, time translation invariance and space translation invariance. Okay, so now here's the big step. So suppose I have a diagram where I have now you see the Green's function here. Instead of writing as I've done for up to now 1, 2 like this, I can write a single Green's function with k like this. Okay, so this is just the Fourier transform of this. Now suppose I have a vertex like this, k1, k2, and whoops, and I have the potential here. Okay, For the Green's function, I have no choice. I mean, I have to have an arrow and it goes in one direction. It goes from the destruction to the creation operator. But for the potential, it doesn't matter. I mean, there's no arrow. I mean, V12 is equal to V21. It's not true for the Green's function, but it's true for the potential. So I arbitrarily choose a direction. Okay, so I choose a direction, let's say like this with Q. Okay, so suppose I start from a diagram written in space-time, where I have to do some integral. We know that in space-time I have to do integral over coordinates like this, right? So if there's a vertex with Green's function coming in and interactions coming in, interaction should be red, then I need to integrate over this point. So what will happen when I integrate over this point? I will get momentum conservation at every vertex. So to see this, we can start from here. So suppose I'm writing that this Green's function, I'm writing like this. You see, I have a G that one 2 bar, but I write it as an integral over some G of K, so K1. And this one, the same thing. This one starts at 2 bar, but there's a G of K2, and I do the same for this Q here. So what happens then is that I get the integral d cube x2, and I get integral from 0 to beta d tau 2, and I have E. Okay, you have to imagine that I have each of these Green's function has some integral. Did I do this correctly? Oh, I did this wrong. Sorry. Wow. What a mess here. Okay, you must be just as tired as I am because nobody saw it, right? Okay. Okay. So you have to imagine that I'm writing G12. Now I'm integrating over this coordinate here, 2 bar. I just wrote 2 here instead of 2 bar. And every one of these objects here, I write, there's some integral over K to do, okay? But I don't write the integral over K for now. I just write the exponentials. So I will have e to the minus I K1 minus K2 plus Q times x2. And then I will have minus plus I of tau 1 minus tau. Sorry, what am I doing? Trying to do things too quickly now. K1n, that's Matsubara frequency, fermionic. K2n minus plus Qn, fermionic frequency, times tau 2. Okay. So you will see this integral over x2 will give me 2 pi cube. It will help me to do the momentum integrals after that. So it will mean 2 pi cubes times delta of K1 minus K2 plus Q. And this integral over d tau 2 gives me beta times the Kronecker delta of K1n minus K2n equal to Qn. And that works out because the difference or the sum of two odd numbers gives me an even number. Okay, So it's possible to work it out this way. So if we conclude then, we have, if we go to momentum space, momentum and Matsubara space, we need to conserve momentum at each of the vertices. Okay, so if I do that, for example, let's go back to these diagrams, and let us write them in momentum space now. Okay, now I will have density at point 1 minus density at point 2. So I take the Fourier transform of that. So it's as if I had some momentum Q that was flowing through this diagram, momentum and frequency. Now here I have, so if I have some momentum Q that's coming here, this means that this has to be K plus Q and this has to be K, okay? So I conserve momentum at the vertex. But now I have to integrate over K because that momentum is not determined by anything, okay? And you remember I started with integrals over everything in sight here, okay? I replaced all the Green's function by integral over K here. Okay, so here this one is very simple. So this one, it's the same idea. So we get rid of this. Then we have, oh, I should have had more space. So I have, let's say, K plus Q here. No, the other way. I have no choice. Let me make some room. So I have some momentum Q flowing. So I have K plus Q here, and I have K here. Then here is the same thing. So I have momentum Q that's flowing here, and I have K plus Q and K here. And here I have K prime plus Q and K prime, okay? And here, I have momentum Q flowing, so I have K plus Q and K here. And here I have K prime plus Q and K prime. Okay, that will allow a momentum Q to go out. But so here what happens in this interaction? Well, now for the interaction, I need to conserve momentum there, right? So it means that the interaction here is K minus K prime. Or K prime minus K, it's even in K, okay? So we're all set now to do, oh, for once I finished what I was supposed to finish. So we'll be ready to compute these diagrams there and see the consequences and everything. Okay, any questions? So you will see on Moodle, I have put a new version of the notes, which are more up to date. I removed some misprints. And there's a homework for 2 weeks from now. Okay. Any questions? Okay, so I will stop the recording and you can stay and ask me some questions. Otherwise, we'll see you